All right, so today we're going to look at the last section in chapter 4, which is talking about how to convert between the different bases or the different number systems. Primarily, we're going to be looking at some of the computer systems that we're familiar with. So we have general base conversions, and then we have our computer math applications of this. So when we consider other bases than base 10, we usually write out the number with the base as a subscript next to it. In this case, we're typically writing the subscript as the word as opposed to a number. So you might see it the way that you see it written here, or you might see it as a number written like this. Now, we do not read this as number 54 because 54 would assume that we're in base 10. And since we're not in base 10, we have to read this as the number 5, 4 in base 8. So again, do not read that as the number 54 like we would in a base 10. Now, when we're dealing with bases, remember again, we have our typical number system that you're familiar with, the Hindu Arabic. This first category is 10 to the 0 power, which is 1. And then we have 10 to the first power, which is 10. We have 10 to the second power, which is 100. 10 to the third power, which is 1,000. And 10 to the fourth power, which is 10,000. And this is what we call base 10, or decimal number system. In a base 2 system, which we call binary, we use 2 as your base. So this would be 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. So 2 to the second power, 2 to the 0 power is 1, and then 2, 4, 8, 16. So binary is what we use with computers. Computers store all information in a binary number system. Another number system you may see occasionally is base 5 and base 7. Base 8 is another very common one in computer programming, and base 8 is called octal. Sorry, to spell it right. Okay, so octal is base 8, and base 16 is another very common one in computer programming, and that's called hexadecimal. Base 16, we're going to look at another example. You see base 16 numbers when you're looking at any HTML programming that you may have done, especially when you're talking about the colors. If you're trying to set the background color for something, you'll notice that the background colors are typically written with letters like A, B, C, and 1, 2, 3, things like that. Those are considered hexadecimal numbers. So with a base 2 number, depending on the size of the number, the largest power you could get would be 16, whereas in mathematics, the largest power right here that we see on the chart is 10,000. So there's a big difference between being able to get a number that's 10,000 and being able to get a number that's only 16. So these are things to think about in terms of the number systems. So when we want to convert to bases, so if I have the number 2134 base 5, and I want to go to base 10, then what I have to do is look at each place in this number and say the 4 is in the 5 to the 0 place. The 3 is in the 5 to the 1 place. The 1 is in the 5 to the 2 place. And the 2 is in the 5 to the 3 place. So you can either look at your chart or you can do your calculations. So that means the 2, and we did this earlier when we did our base 10 expanding. The 2, there are two 125s because 5 to the third power is 125. There is 1 25 because 5 to the second power is 25. There are 3 5s, and there are 4 1s. So if we work all of this out, we have 250 here, we have 25 here, we have 15 here, and we have 4 here, and if we add all of that information, we get 294. So the number 2134 in base 5 is equivalent to the number 294 in base 10. So that's what we were doing earlier when we were expanding out a number. All we were doing is multiplying it by its place value. And in our case, with the Hindu Arabic, we were familiar with the place value as being 1, 10, 100, 1,000, 10,000. So then here we have another one. To convert from another base to a decimal form, this is what they call a calculator shortcut. So what we're going to do is we're going to take the first digit on the far left-hand side of the number, and we're going to multiply it by whatever base it is. Then we're going to add the next digit, and we're going to multiply by the base again. And we're going to keep doing that, and what we're going to end up doing is add the last digit on the right, but don't multiply that last digit by the base. So let's look at this. We have 432,134 in base 5, and we want to go to decimal. So we're going to follow the steps of the problem, and we're going to take the number on the far left, which is 4. We're going to multiply it by 5. So we've dealt with this number right here. And then we're going to add 3 to that. So we end up with 23. And then we're going to multiply that by 5. And so we end up with 115. And then we're going to add 2. So now we've dealt with all these numbers. So we get 117, multiply it by 5, and we end up with 585. Now we're going to add the 1 with our next digit, which is 586. Multiply it by 5, because again we're in base 5. We end up with 2,930. We're going to add that 3 that we haven't added yet. Mark that out as we go. We get 2,933. Multiply that by 5. So we end up with 14,665. Add that last 4 on, and we get 14,669. And this is our answer. Now again, we could do it the same way that we did the other problem. This would be multiplied by 5 to the 0 power. This would be multiplied by 5 to the first power, 5 to the second power, 5 to the third power, 5 to the fourth power, and 5 to the fifth power. So you can also do it that way, and you will get the same answer as the 14,669. So this is just showing you that expanded form, but this is a calculator shortcut that you would probably want to use a calculator for to make it a little bit simpler. Okay, so here's another one. Let's say I wanted to convert the number 7,508, which is understood to be base 10, so since there's no base written next to it, and I'm going to convert that to base 7. So the way that you convert from base 10 to any base is you take the number that you've got and you divide it by 7. So 7 divides into 7,508 1,072 times, with a remainder of 4. And then we keep going. 7 divides into 1,072 153 times, with a remainder of 1. 7 divides into 153 21 times, with a remainder of 6. 7 divides into 21 3 times, with a remainder of 0. And 7 divides into 7 divides into 3 no times evenly, with a remainder of 3. So our answer to this problem would be the number 30614 in base 7. You write the numbers down backwards. Okay. So this is really common. When you're thinking about a computer has to have the ability to convert a number to binary so that it can store it on its hard drive. But the computer also has to have the ability to take that binary and convert it back to decimal so that you understand the numbers and you're not looking at a bunch of ones and zeros. So in binary or in computers, we have what we call compilers, and that's what a compiler is designed to do, is convert numbers back and forth from binary to decimal and from decimal to binary. And if you think about HTML, a lot of times you have special packages that will allow you to do that, and those are also called compilers. Okay, so if I wanted to convert from, say, binary to hexadecimal, many people think that the easiest thing to do is to convert from binary to decimal and then take decimal and go to hexadecimal. And typically that's usually the easiest thing to do. So again, let's say that I had an HTML program and I wanted to pull the HTML program up in a language that I could understand. So we would want to take that hexadecimal code and we want to convert it to probably decimal. But then in order to save it onto the computer that I'm using, I have to convert it to binary. So it's a lot easier in most cases to convert to decimal and then convert to binary. Okay, so some of the most common number systems that they use in computer math are binary, which is base 2, octal, which is base 8, and hexadecimal, which is base 16. So in binary number system, there are only 2 digits used, and it's the digit 0 and it's the digit 1. So in the decimal number system that we're familiar with, we have the digits 0 through 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. In the octal number system, they have the numbers 0 through 7. So what happens in binary, if you can imagine this, with binary, what would happen is that the number was either turned on or off. So if you think about switches, the switch was either on or off. And so it became very, very easy in the days of programming to design computers that were using switches. And either the switch went true or false. If you think about the switches that we were using in the logic section. So binary became a very easy system to think in terms of programming computers and creating computers. And it's one of the big reasons that computers have evolved into small handheld devices. The original computer that was the very first computer that was created, the ENIAC computer, just in case you wanted to look at that up, that's spelled ENIAC. The ENIAC computer worked on a base 10 number system, so it expected all the numbers to have digits from 0 to 9. So the ENIAC number, or the ENIAC computer, used something called vacuum tubes. And a vacuum tube, if you can imagine, looks like a light bulb. And there would have to be 9 vacuum tubes for every place value. So you would have to have 9 vacuum tubes for the zeros place, the ones place, 9 for the tens place, 9 for the hundreds place. And they were very powerful machines. Powerful in the sense that they used a lot of electricity. They were very cumbersome, and a computer in those days could take up an entire, to give you an example, the entire top floor of FAC2 at Germana would be the ENIAC computer. And all it could do was add, subtract, multiply, and divide. So the simple 4-function calculator that you can go to the store and buy for a couple dollars was the size of the top floor of FAC2. So there's a big difference between what we have, and that's why the systems have evolved from decimals to binary to octal. And again, some of the things like using hexadecimal involves having the ability to use bigger number systems. So here we want to convert the number 111 001, which is base 2 or binary, to decimal. So we can use their system, but I'm really familiar with this one. So we have the 2 to the 0 power, 2 to the first power, 2 to the second power, come up here, 2 to the third power, 2 to the fourth power, 2 to the fifth power. So we have 1, 1. We have no 2s. We have no 4s. We have 1, 8. Excuse me. We have 1, 16. I'm sorry, I have to slip down here. And we have 1, 32. So if we take all of these numbers and add them together, 32 plus 16 is 48. 48 plus 8 is 56. 56 plus 1 is 57. So the number 111001 is the number 57 in decimal. Now the way that you're seeing it here is using the calculator shortcut. So we took the first number and multiplied it by base 2, then we added the next digit on, and we continued on through that, and we still ended up with 57. So you can choose to do these by either method, either using the expanded form like we did earlier, or using the calculator shortcut like you see here. So, of course, I have to throw in one little joke here. There's a very common joke that says something like, there are only, here's what it says, now I'm hoping that when you look at this, you'll read this correctly and say there are only 10 type of people in the world who understand binary, you and me. So think about, what does this number represent in binary? It represents the number 2. So this is a really common joke that you might see out there on people's t-shirts and things, and now you'll understand that joke better. All right, so the next one, how to convert from hexadecimal to binary. So hexadecimal is one of those interesting number systems that not only uses the digits from 0 to 9, but it also uses 6 capital letters A, B, C, D, and E, and F to represent the digits, in their sense, 10, 11, 12, 13, 14, and 15. Hexadecimal is a base 16 number, so it has the digits technically from 0 to 15. So it has to be able to represent these 2-digit numbers as letters. So that's why you have the letters A, B, C, D, and F. So when you look at this problem, when we want to convert 8B, 4F from base 16 to binary, what some people find easier is to take this number and convert it from base 16 to base 10, and then take the base 10 and convert it to binary. But there is a shortcut. If I take these numbers, oops, and I convert each of these into 4-digit binary numbers. So the number 8, I want you to think about these 3 numbers, 1, 2, 4, and 8. So if I had to have a 4-digit number that represented 8, I would need an 8, and I would need no 0, no 4s, no 2s, and no 1s. So the number 8 is 1000. B is the number 11. So in order to get 11 from this combination of values here, I would need an 8, a 2, and a 1. So 8, I don't need any 4s, and I need a 2 and a 1, and that equals 11. To get the number 4, I need no 8s, 1 4, no 0s, and no 2s. To get the number F in binary, I would need all 1s. So then if I put all of that together, I end up with 1 0 0 0, 1 0 1 1, 0 1 0 0, 1 1 1 1. So the binary representation of 8B 4F in base 16 is the number 1 0 0 0 1 0 1 1 0 1 0 0 1 1 1 1. All right, you just need to look over this section in the book, make sure you're really comfortable with it. It can get a little bit confusing, but if you read all the information and study those examples, I think you'll be fine. Email me or text me if you're having problems, and we'll get together and work on this. Have a great week.